Buongiorno,
Buongiorno Francesca, come stai?
ciao, bene, buongiorno.
Eh,
Tu?
bene, bene anche. Con tante cose, ma bene, siamo.
Dai,
Che
lo so.
ti voglio domandare una cosa.
Sì.
Farei una pausa o lo farei direttamente tutto continuo?
Allora, io in realtà ho programmato due pause, cioè dividerei le 3 ore in tre blocchi e lo
D'accordo?
faccio vedere all'inizio. Ho fatto una specie di programma, così si spezza un pochino sia per loro per
Sì,
fare un attimo, prendere un caffè, qualcosa,
sì,
sia
sì,
per
sì,
me,
sì.
ma così
Come
è
tu
più
vuoi,
organizzato.
tu hai la libertà di farlo come tu vuoi, senza problemi.
Ok, grazie. Ho già caricato la presentazione sul Drive Google, il PDF,
Perfetto.
così già...
L'hai inviato per correo, per email o...
No, l'ho messo direttamente sul Google Drive, quello di
D'accordo.
Adriano.
Perfetto, perfetto. Che Adrian credo che ti ha inviato il link del Google Drive.
Sì, sì, sì,
Perfetto.
sì, sì, esatto, esatto.
Perfetto. Ah, ti devo fare che tu sia la co-anfitriona, non so come si dice in italiano, co-anfitriona,
Organizzatore.
co-organizzatore.
Sì,
E,
sì,
si può
così
assaggiare
posso...
che vuoi compartire?
Sì, 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 proviamo subito.
Sì,
Allora. Allora, provo a condividere solo il PowerPoint, vediamo se funziona bene, se no
sì,
condivido tutto lo schermo, non c'è problema.
perfetto.
Allora, vediamo.
Finalmente abbiamo deciso di farla in inglese perché pensiamo che più della gente parla inglese che italiano e chi no, che ne
Ah,
parlano inglese, dopo faremo la traduzione con i sottotitoli e se le invierà
sì,
agli alunni.
sì, sì, no, ma per me va benissimo, l'importante è appunto saperlo, giusto,
Sì,
anche ora possiamo
sì.
cambiare idea se vuoi, non è un problema.
Saperlo prima, per lo meno. Sì.
Un minuto prima,
Sì.
un minuto prima. Senti, tu vedi
Sì,
bene
sì,
la slide di copertina? Proviamo, adesso vedi il programma?
sì,
Ok, e allora funziona, dai,
sì, sì, va benissimo, sì, sì, senza problema.
funziona, sì, ma vedi anche una finestra nera che copre la diapositiva?
Come? Non ti sento bene perché abbiamo molto ruido qua, ma dimmi, dimmi.
Vedi, vedi anche un box nero sopra la diapositiva? O no?
No,
Ok, ok,
no, no, io lo vedo
perché...
bene.
Ok, ok, perché io vedo un box con il mio video e il tuo video in questo momento,
No,
sopra la
io lo
diapositiva.
vedo, ti vedo a te e a me la parte sopra e la diapositiva sotto.
Ah, perfetto,
Sì.
perfetto, perfetto. Ora sì, 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 sì,
Sì,
perfetto.
ma adesso ti dico, cominceranno a introdurre gli alunni perché
Sì.
come non sapevamo fare bene la gestione, posso che tutta la gente può incorporarsi nel momento che vogliono.
Perfetto, perfetto.
Sì. Ma sì, va bene tutto, così tranquilli, e
Sì, sì,
nessun problema. Se
sì, sì.
puoi lasciare di compartire la...
Sì, sì, la lascio
Sì,
attiva
sì, sì.
così,
Sì, ma non la...
così.
Ah sì, 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 prima l'hai posto screen, pantalla
Sì, sì, sì. Sì,
completa.
lo metto a
Sì, sì.
screen, appena ci serve lo rimetto a screen. Ma quanti studenti ci sono?
Sono 21. ma
Ah,
per le mattine generalmente si connettano meno. E oggi in inglese non lo so,
siamo
perché,
io e te
perché non lo
e
so.
Margherita. Ho
Non lo
visto che
so
è arrivata la
nella
prima.
Italia perché forse parlano più lingue, ma adesso la gente giovane parlano molte lingue, ma la mia generazione non ha abitudine di parlare altre lingue. Inglese più
Però
di
tu
me.
parli italiano.
Sì, sì, io
Tu
parlo
parli
italiano
italiano.
e inglese un po' anche, ma la gente io non sono sicuro quanto alunni avremo.
Va bene, non importa. Uno
Perlomeno
c'è.
abbiamo una, Margarita.
Sì, sì.
Significa che abbiamo una.
No, ma va benissimo. E la cosa buona è che hai trovato un modo tecnico per poi fare i sottotitoli
Sì,
nella
sì, 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 sì,
traduzione.
perché non sapevamo, al comincio non sapevamo come fare, perché in italiano è molto difficile Italiano e lo spagnolo puoi capire più o meno, ma quando è una
Sì,
lezione è difficile
lo
seguire
stesso.
tutto il tempo, 3 ore in altra lingua, no, non è facile. In inglese dipende del livello di ognuno.
Mm.
Verremo.
Sì, sì. Comunque le diapositive, la presentazione io l'ho condivisa, quindi tutte le informazioni possono essere riguardate lì dentro, quindi non c'è problema. Piano piano con il traduttore.
Sì, 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 ma sarai i sottotitoli e spero che tutto via bene, sia bene.
Speriamo.
Eh,
Speriamo.
e tu lavori nel centro? Ah, una cosa, il tuo cognome
Sì,
è Cigna, no?
Cigna.
Cinna o
Cigna.
Cigna? Cigna, Cigna.
Cigna.
E io
Cigna.
credevo che si pronunciava così, ma è meglio
Ma,
assicurarsi.
ma non ti preoccupare.
Ma lavori da molto tempo fa nel Consejo Nazionale di Investigazione dell'Italia?
Lì da 4 anni.
Ah,
4
4
anni.
anni. D'accordo. Sì, sì, sta bene.
Prima ero all'Agenzia Spaziale Italiana.
Ah sì, che interessante.
Mm. Sì, 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 sì. Sì, sì, tutto molto bello.
Se vuoi lasciamo di compartire e in 3 minuti cominciamo. D'accordo?
Sì, sì, sì.
Sì,
Ho
comincio.
visto che già stai
Sì,
registrando.
sì, se vuoi comincio io e spiego un po' lo dei sottotitoli che si invieranno
Sì,
il
sì, sì,
video
sì.
un altro
Sì,
giorno
sì, la parte
e, e
pratica.
ti,
Sì,
e ti passo la parola a te,
sì, sì, sì,
d'accordo?
sì, tranquillo, perfetto.
Bene,
Grazie.
a te. Ma io seguo vendo la tua pantalla che stai compartendo. L'hai lasciata di compartire?
Sì. La
E
vedi?
anche la guardo.
Non si vede?
No, ma vedo la tua presentazione.
Sì. Io ho il video e la presentazione attiva.
No, ma dico che se le puoi lasciare la presentazione adesso.
La posso chiudere, dici? O la lascio aperta?
No, no, chiudela se puoi.
Ok, sì,
Ah, adesso.
ok.
Per cominciare che si la presentazione a me e dopo a te e già la metti
Sì, sì,
lì
sì,
dopo.
perfetto.
D'accordo? Buenos días, Francesca. Sí.
Buongiorno.
Buongiorno, buongiorno. Bueno, voy a comenzar comentando con los alumnos que se os envió un correo electrónico diciendo que la lección de hoy, la clase de hoy sería en inglés. Para el que tenga alguna dificultad para seguirla en inglés, porque decidimos si hacerlo en italiano o en inglés, al final hay más posibilidades que haya alumnos que sepan inglés. Y entonces lo que haremos va a ser que se grabará igual que todas las clases anteriores, pero después se enviará con los subtítulos en español, para que todo el mundo pueda comprender lo que a lo mejor se le haya podido escapar. De todas maneras, ella va a ir poniendo las presentaciones, entonces más o menos yo creo que se podrá seguir sin problemas. Así que, bueno, presentaros únicamente a Francesca Chiña, que es investigadora principal del Consejo Nacional de Investigación de Italia y es experta en teledetección aplicada con experiencia en InSAR aplicada al patrimonio cultural. Así que, bueno, simplemente quiero darle ya la palabra, agradecerle e, bueno, non so se parlare in italiano, grazie tante Francesca, e puoi cominciare la lezione quando vuoi.
Grazie a te. Thank you very much and welcome everybody. I'll share my presentation. So you should see the slides now. Can you?
Yes, we can.
Yes, yes, we can see the presentation.
Okay. Is it in presentation mode in your screen?
Yeah.
Wonderful. So thanks again and welcome everybody. My name is Francesca, as per the introduction, which I'm grateful for. So this is module 4.1, which is the first half of this particular module, focused on the presentation of a number of case studies involving the use of SAR data and InSAR applications for cultural heritage. So I'm in charge of this module today, whilst on Thursday, Jose Manuel Delgado from the European Space Agency will go through other case studies in Spanish. So this module has been organized in 3 different parts because we have 3 hours. It's a long time, but we can split that considering different case studies and different topics involved in the application of radar and InSAR in cultural heritage and archaeology. So we've started with introductions already. So soon I'll go through part 1, which is focused on the use of SAR in archaeology with examples in Peru and in Syria, looking at the mapping of heritage sites and landscapes changes, and also monitoring archaeological looting. After each block, as you can see here, there will be some time for questions and answer, and then a short break. Regarding questions, I'm happy to take questions during the presentation, if you prefer, or at the end of each part, if you are fine with that. It's really up to you. There are no problems, and you can either ask questions with the microphone or also type them in the chat. For me, it's absolutely the same. You can type them in Spanish, you can speak in Spanish, I can understand, but the answer will be in English because my Spanish is not that good. So this is the structure. So part 1, then we will have part 2 focusing on Iraq. And then part 3, looking at how to exploit InSAR data to develop some risk assessment workflows in central Mexico and Italy. So we start with part one, and this is probably a recap, like a summary of information that you have already seen before in the previous modules. So this is an overview of all SAR missions starting from the late 70s, and showing you the amount of opportunities that we have today in the different radar bands, so the different frequencies and different wavelengths, with an increasing volume of SAR data that can be exploited for a number of applications in archaeology and heritage. And I must say this plot is already old. I mean, it was created in 2018 or 2019. So some missions are even missing, like here, it's missing a full group of missions from another frequency band of SAR, so the S band, like InSAR, that was launched actually a few weeks ago, and it's carrying both an L-band and S-band radar. So this is an overview, but it's continuously updated by the experts. So every time you have a new mission, there is an update to this plot. So plenty of opportunities for heritage applications. But what is the actual opportunity that we can exploit for such applications? So in this figure, we have tried to group the different opportunities that we have by distinguishing 4 different blocks. So archaeological prospection, topographic surveying, environmental monitoring, and condition assessment. So basically, as you can see in this list, with radar data and advanced processing methods, we can do many things that can be useful for these applications. First of all, feature detection, delineating, mapping heritage sites, archaeological sites, old buildings. We can do topographic surveying by creating DMs, so digital elevation models, using advanced processing methods involving SAR interferometry. We can study and discover buried structures underneath thin layers of sand or soil. We can go through paleo-environmental studies. But we can also look at conservation and preservation by monitoring our heritage sites. We can do looting monitoring, so damage by illegal excavators. We can do condition assessment. We can also look at natural and anthropogenic geological hazards, for instance, linking with land subsidence or landslides and other processes involving also human actions. And as I said before, we can do environmental landscape evolution. So in this presentation, I'll try to show you a few examples of everything, so you have a flavor of all the opportunities available today. So first of all, like the proof, the scientific proof that this type of data has been increasingly used in the field of archaeology and heritage. So here, now, almost 10 years ago, we started to plot the number of publications involving the use of SAR for archaeology and heritage. As you can see in the black line, there has been an increase in the first years after the launch of the first SAR missions, and then a boost in 2 particular moments. So at the end of the 2000s, so in 2003, when ESA, the European Space Agency, signed an agreement with UNESCO to promote the use of space technologies to support the World Heritage Convention, but particularly in 2011 and the following years, where a number of special issues in scientific journals were launched. So the scientists had the opportunity to publish the first studies involving the use of this data for heritage and archaeology. So I know in the previous modules you've been talking a lot about the use of SAR, but particularly InSAR. So in my presentations, I'll go through examples of both InSAR applications, but also the use of SAR amplitude. So I don't know if you've heard about this parameter. Basically, is the strength of the radar signal that any surface is capable to scatter back to the radar sensor during the acquisition. So usually is displayed as a gray, black and white, grayscale image, showing you for each pixel the amount of this radar backscattering. So this can be transformed into physical units. It's typically called the sigma naught. And this parameter depends on both the properties of the radar signal, so the type of polarization, the wavelength, the frequency, the incidence angle, but also, and most importantly for our applications, the properties of the scattering surface. So the roughness, so the microtopography, the shape, and the dielectric properties, the soil moisture, and things like that. We will see that in the next slides. So first applications in paleo environments. So this is probably the first example of scientists trying to understand the potential of SAR for archaeological and paleo environment applications. So in the figure here, you see a Landsat image. So it's an optical multispectral image of a desert area in Sudan. As you can see in this image, you can only see the desert. You cannot recognize much features, but when they overlapped the SAR image of the same area in this particular area of interest, this is what they saw. So here you can clearly see the power of this type of data. So in the radar data, you can recognize a number of dry rivers and paleo channels thanks to the radar penetration capability. So why is this possible? We can understand that using these other examples. So it's similar to the previous one. This is an optical image to the left of the desert. And this is the corresponding radar image in L-band from ALOS Pulsar mission. As you can see all these channels in black and all the other micro topography features in gray and also towards white colors. And here you have the plot explaining why this is happening like that. So every time you don't have a channel, basically the radar signal penetrates the thin layer of sand and is capable to bounce back with a strong return to the radar sensor. Other times where you have when you have a channel, so the dark features, this is what happens. The radar signal penetrates the sand, but also penetrates the alluvial sediments of the ancient channel up to coarse deposits at the bottom of the channel, and most of the signal is lost during this penetration phase. So you have a weak return to the satellite sensor and dark areas. So this is in very simple terms the process that is happening, and it's allowing us to see what we see in the images. This is another example of imaging of paleo environments. This is a famous area. So it's the Nile River in Egypt. As you can see here in the optical data, even if it's black and white, in this desert area, you cannot see any features. Whilst if you look at the same area with radar, this is what you see, going through penetration through the sand. Basically, it's the radar reveals a paleo channel of the Nile River, which was invisible to the optical data. So another example here, looking at the area of Angkor Wat in Cambodia. This is a Google Earth image, so even very high resolution cannot allow such a view like this provided by SAR data. So here you see how well the artificial channels, but also the reservoirs of the site are depicted. You can even recognize the microtopography and more articulated river channels with this data. But of course, the interpretation sometimes is quite challenging, as you will see in other examples. But when we look at archaeological sites and archaeological features, radar confirms, proves very strong capabilities in detecting signals relating with archaeological remains, archaeological ruins in the subsurface. For instance, here I compare a radar image from the Cosmos SkyMed mission. So this is a 1 meter resolution, and the same acquired by very high resolution data like Google Earth imagery of the same site. As you can see, not only in the optical data, you see these damp and soil marks due to the presence of a buried circular fissure, but also in the radar data. So the capabilities are sometimes similar, but also in other times are also complementary, as we saw before. It's not just about soil and damp mark, so soil moisture difference, but also about vegetation differences. I'm sure you are familiar with the concept of crop marks. So they are differences in local vegetation due to a number of differences in the underground, for instance, due to the presence of a paleochannel or a linear structure like an old road or even old buildings underground. So every time you have such a difference underground, the vegetation grows at different rates, and also different types of vegetation grow on top of these structures. So here in the radar, you can recognize the difference in the vegetation due to the presence of this paleochannel in an archaeological site in southern Italy. Another example is about detecting shadows. It's not very often that SAR to detect shadows, because usually we exploit the data for the previous applications that I showed you before. But here in China, they exploited SAR data. I think it was from the Cosmos SkyMed mission at 3 meter resolutions in this case, and they exploited the data to depict the topography of this ancient feature. And as you can see, we can even see the shadow of this wall in the radar data. This is an example of processing radar images. So we use typically the raw images as they are, so the amplitude signal in sigma naught, but there are a number of filters, spatial filters, for instance, in this slide, that can help us to enhance the features that we can see in the image by decreasing the typical noise of radar data, which is called speckle. It's like salt and pepper, so white spots, black spots, all mixed up on top of the good signal, let me say. And using these spatial filters and testing them for your particular area of interest, you can enhance the visibility of your archaeological features of interest. So it's about spatial filters, but also you have the possibility to use multitemporal filters. Like in this case, in southern Italy, we used 2 different types of enhancement. So a spatial enhancement, similar to the previous slide, where we implemented a spatial filter going, like, let me say, scanning the image and averaging nearby pixels to remove some of the noise. But as you can see, you lose a bit of the spatial resolution. So here, yes, you clean the image from the noise, but then you lose a bit of the detail of some of the features. If you, on the other hand, have several images of the same area acquired with the same geometry, very close to each other in time, you can average them in time, and you can enhance the quality of the signal up to this level. As you can see here, we can even see the shape of the ruins, the shape of the coastline very clearly. We can recognize these white spots, which are the artificial corner reflectors installed at this site. So it's an opportunity. This is to show you the opportunities offered by this data. So we also have phase in the radar signal. I'm sure you've heard a lot about using SAR phase. So it's a quantity telling us something about the sensor target distance. And if you have two different images of the same area acquired with the same geometry, but at two different times, you can create interferograms, as you've seen in the past modules, and extract components of interest, for instance, topography and deformation. Why do you do that? Very, very briefly, it's a recap to generate the digital elevation models. So to extract topographic features, the topographic component, which is of interest for archaeological applications. I'll show you later. You can do ground motion monitoring. You've heard about that in the previous modules many times. And you can also consider the component of the coherence. I don't know if you heard about coherence. In very simple words, it's the amount of change. Well, it's the opposite. Actually, it's a parameter telling you how similar two images are from time 1 to time 2. So the closer to 1 the coherence is, the more similar the two images are. Whilst if you have a change, you have numbers of coherence approaching 0. But we will see that in the actual examples. So we start here with the first full example that I'm showing you today, which is about the famous Nazca lines in Peru. So I'm sure you've heard at least once in your life about this area. So we are in the period of the Nazca civilization, when the populations of Nazca built up and lived in this wonderful landscape involving the Rio Grande River catchment basin. And this site involves a number of heritage features. First of all, the Nazca lines, as you know, the geoglyphs of Nazca, but also sites like this one involving urban constructions like the ceremonial center of Kawashi. Basically, it's mainly like mud-like material, but also aqueducts like the Puquios and Ojos. So they are drainage galleries and reservoirs, respectively, that were used by the Nazca civilization to move water and to catch water for daily use, for agriculture, and so on. So in this particular case study, what we did is to start from the single look complex data, so amplitude and phase information. We performed co-registration and radiometric calibration of all the data to a single reference image. We used an external DM to support the image processing, and created a number of derived products, and I'm showing you them in the next slides, but also resampled multi-look intensity images in the radar geometry. And then the final output is obtained by converting everything to map geometry. So WGS 84 coordinates or UTM coordinates. So anything that you can put in a GIS project and can be compared and integrated with other geospatial layers. So here an example of how the Rio Nazca looks like. So in the photo, you can see the river course is mainly vegetated. Then you have a sharp transition with the desert, with sparse vegetation, some trees, and then you have, for instance, the ceremonial center of Kawachi or other urban structures like in this case. What you can see in the comparison between an optical data visualized in false color combination, so involving near-infrared, red and green channels combined together, compared with a radar image of the same area, you can recognize the river Nazca. You can recognize small water basins like this Pozo Cocha here. You can also see the airport runway, this black feature, the Nazca town, and many archaeological fields, the same that you can see in the multispectral data. Moving a bit to the south, this is another comparison of an optical image, an overview of this Cerro Blanco mountain, which is all composed by sand. There are a number of dune ridges at the top. Here you see the mountain in the optical data, and here the same mountain in the radar data. And this is all in black for the physical reason I explained before. So most of the radar signal penetrates this thick layer of sand and gets lost within the sand. So you have basically no signal coming back to the radar sensor. So this is why you see a black area, but yet you can recognize all the dune ridges because they are acting as natural corner reflectors to the radar signal. So you have a bit of signal bouncing back to the satellite in this area. So what we can do to do change detection studies. So this is an example of very simple change detection approach. So you take two images of the same area acquired at two different times. You take the amplitude information and you create a color composite of the two images. So every time the first and second image will have the same value in that pixel, it will appear in gray or dark gray or black. But in case there is a difference in the amplitude at that particular pixel in one image with respect to the other one, you will see colors. So in here, for instance, you see in light blue, so in cyan, this color here, you can recognize a brighter signal in the image acquired in 2005, which is due to some water flow underground across these puquios in the Taruga Valley. And as you can see here, you see a number of soil moisture changes along this branch of the river and even along this branch to the south. So it's an interesting approach to use the data in a very, very simple way. If you have more than two images, for instance, you have three, you can do something similar. You can combine the three images acquired at three different times through a green, blue combination, so it's RGB. And every time there is a change or a brighter signal in one image or the other one, you will see that color. So this is, for instance, due to a number of changes, like due to dune migration, like sand migration, caused by wind, mainly in this sand dune. So another approach, instead of color combining the data, you can also do more advanced processing. The first one to the left is called ratio. So you can ratio one image to the other one. So this is date 2, for instance, and this is date 1. So one after and one before, you have these two images. If you do the ratio between the two signals, you will see that any change will pop into very positive or very negative values. So every time, for instance, there is an increase in the brightness of the radar image, you will have a positive value. Every time there is a decrease, you will have a negative value. And then it's up to you to go through interpretation of these signals. For instance, in here, they are due to soil moisture changes, mainly along the river. But in this particular case, they are due also to human activities, both legal and illegal, unfortunately, at the site of Kawachi, at the ceremonial center. To the right, we see something similar. So this is the other approach to change detection. Change detection can be done through coherence. As I briefly said before, you can exploit the interferometric coherence between two images, which is a parameter derived by accounting mostly for the phase of the radar images, and you can quantify the change through this index called coherence. And in this case, you can see most of the change is along the river, but this triangle here is linking with what we saw in the other change detection products, so human activities at the site of Kawachi. More in detail, this is what we did by comparing a number of different images acquired at different times for this particular site. So we exploited both descending mode data and ascending mode data, and these different combinations of interferometric pairs to study a bit this change at the site and trying to understand the exact time period when this change occurred. So something else was to focus exactly on the site using these MVSAT images acquired between 2003 and 2005 at 30-meter resolution. And as you can see here, even with this coarse, low resolution, we could depict some signals of interest. In particular, some of them were at this pirámide naranja here, and also to the bottom, to the southeastern corner of this sector B, where there are a number of archaeological mounds, and also to the east of sector A, east of the Grand Pyramid at the site. And unfortunately, by comparing these observations with archaeological informations and records, we know that some of these changes were due to looters, so illegal excavators trying to find archaeological goods at the site, and so damaging the archaeological and heritage assets of the site. I'm transitioning now to this slide because I want to show you the power of spatial resolution. This is an overview of the Pampa, the Nazca Plateau, let me say. And here you can recognize the linear features of the Nazca lines. You can also recognize these features here, which are rectangular features of the Nazca line, and also this road, which is the Panamericana Sur, one of the main roads crossing the plateau from north to the south. And this is very, very clearly depicted in the radar data. But what happens when you move from lower resolution data to higher resolution data? We start from the top. Here we have a TerraSAR X ScanSAR image at about 18 meters resolution. And then in C, we have the same area depicted in strip map mode with 3-meter resolution. Then we move to spotlight mode at 2-meter resolution, and then high resolution spotlight at 1-meter resolution. So you can clearly see the increase in the detail that you can capture by improving the spatial resolution of the data that you use. You can see additional features when you move towards the higher resolutions. So examples of what you can do with high resolution data, for instance, here, this is an example of what we could study in this area, very close to the Panamericana Highway in Nazca. As you can see in the top, we have optical data from Google Earth showing us the situation very close to the highway at 2 different dates. As you can see here, we see this feature. I hope you can see the mouse. But to the right, you can see clearly indicated the illegal mining site that was developed in a few months of time. And here at the bottom, we can see the coherence products derived from Cosmos climate data at 3-meter resolution. And you can see the low coherence, so the correlation feature due to the illegal excavations of the site. So they are clearly depicted by the coherence product. You can even see the access road to the illegal mining site here in violet, because this is very decorrelated in the coherence images. So something else about decorrelation. This is an example of impact assessment linking with anthropogenic incidents very close to the Nazca lines. At the end of 2014, some environmental activists accessed the site to create a message with yellow letters very close to the hummingbird geoglyphs. So since they didn't use the protections for the shoes, basically they walked through the pampa and altered a bit the microtopography of the site very close to the geoglyph. And in here, this is an aerial photograph that was distributed by the media, showing the actual impacted zone with the feature of the path that the activists followed to access the site. And here, some of the exact location of these yellow letters. And here, we did a study with coherence, again, by comparing an image before the event with an image after the event. And even at 3-meter resolution, we could recognize some decorrelation features linking with this incident. This is another example using the same approach. A different type of incident. In this case, this is the Panamericana Sur highway. And in January 2018, a truck went out the road and diverted by crossing some of the plane where the geoglyphs are, and he left very deep tire marks across the landscape. Then he turned here and went back. So here you can understand the damage, like the surface alteration, the surface disturbance that was caused by the tires. And here we can see the study of this incident with Cosmos climate data at 3-meter resolution. Again, we compared an image before with an image after the event. We could even depict the tracks, the full tracks of the vehicle here. So you will see these tire marks correspond to the tire marks that we can see in the image. So in the image, in the photograph, north is at the bottom, and to the top you have south. So the tire marks start from here in the coherence map and then go up to here across the pampa. So here you can appreciate the power of these derived products. Now we go through the second case study, and then we make the first session of question and answers. The second case study is very interesting, unfortunately, very interesting from the scientific point of view, but not very much from the archaeological point of view. So I mentioned before the concept of archaeological looting. Archaeological looting is includes, by definition, any unauthorized excavations with no scientific purpose, but aim to grab goods and sell the archaeological goods to the illegal markets, to illicit markets. So every time you have political crisis or war, this process accelerates at many archaeological sites. Here in the photo, you can see an image of looting in Iraq, and you can recognize the different pits or looting holes created by the diggers. It's a global phenomenon. So it's not just in the Middle East, but it happens in Northern Africa, it happens in Europe, it happens in the US, it happens in Southern America with different rates, with different shapes, with different excavators. Today, we are looking at Iraq, at Syria in particular, and I'll show you the site of Apamea, what we did with radar. Usually, when scientists or archaeologists use satellite data for looting, mapping, or monitoring, they mostly use optical data. As you can see in this plot, this is showing the number of publications in a cumulative way per year, or also the total number of publications per year by splitting them into optical, SAR, and SAR and optical, depending on what the authors used in their studies. As you can see, optical data are the mostly used, while SAR is only used a few times in a few publications, but yet the use is increasing. And here you have the reference for to a review paper that we published on this topic. So if this is of interest, this is a very good paper, not because we wrote that, but it has been recognized as an interesting overview paper of how to use satellite data to detect archaeological looting from space. So today we look at Syria, and in particular, a few hotspots, well, several hotspots of archaeological looting have been identified across the whole country. linking with the occurrence of the civil war in 2011, started in 2011. And as you can see, the distribution is quite worrying and very dense in a number of regions of the country, especially in the northern area. So today we focus on Apamea. I don't know if you've ever heard of this site. It's a very interesting and majestic site, including a very long colonnade called Cardo Maximum with colonnade. And it was inscribed in the tentative list of UNESCO in 1999, but then it was never included in the officially included in the list for a number of reasons. As you can see, the site includes this colonnade, as I said, and then a vast land involving archaeological ruins, tombs, and other heritage features. The situation, unfortunately, starting in mid 2012 was like that. So a number of looting pits were dug across the site. Many of them were even dug using excavators, so bulldozers, by creating a number of looting pits with a clear rectangular or geometric shape. Some of them were very shallow, some of them were very deep, a few meters deep, depending on what the looters found during the excavation. So we call it opportunistic rationale of digging. So it's a varied level of damage across the site. If we look from above, this is the boundary of the site, which is depicted by the Justinian walls, which were built to protect the site. In here, in light blue, you can see the areas that were excavated by archaeologists, so properly excavated by archaeologists as of the first years of 2000 to 2010, 2011, so before the Civil War. And in red, you can see the main archaeological features and ruins of the already excavated areas. What we did was to study the site combining optical and radar. In particular, we used optical data, very high resolution data from Google Earth, to visually identify looting features and do some manual mapping of looting features. We use Sentinel data at 10-meter resolution, Sentinel-2 data, optical multispectral data, to study ranges. And we combine them with radar data from TerraSAR-X and Cosmos Skymed missions. And I'll tell you later in detail what we did with that. And we started our study from the start of the Syrian civil war. So here is a time lapse of what we see with Google Earth imagery since the start of the civil war and going up to March 2014. As you can see here, this is the excavated area, so the legally excavated area. Then in April 2012, we have first clear evidences of looting in the area owned by the government, which was a archaeological site, the excavated archaeological site. Then we have a spread of looting also moving towards the west and involving the cultivated fields to the west. Here in the map, we have summarized the situation of the site as of March 2014 with all the looted areas delimited in yellow. As you can see, almost 50% of the site was already looted by that time. But the question was, well, we can see the spatial distribution of looting, but what is the looting rate? So we tried to address this question using SAR. We launched a very high resolution campaign with TerraSAR X steering spotlight mode, which is an imaging mode providing sub-meter resolution with up to 24 centimeter azimuth resolution, which more or less is 50 centimeter resolution on the ground. We started in October 2014, and every 2 months we acquired an image. So how do the looting holes look like in SAR images? We developed this conceptual model, which is available in this paper that you can access from the web. If you don't have access, you send me an email, I can send you a copy, there's no problem. So we developed this model by accounting for the geometry of acquisition of the satellite sensor, the geometry of the looting holes, and we came up with this model, which is basically creating the looting mark, how the looting appears in SAR data. Every time you have a looting in SAR data, it looks like that. So a looting feature is a coupling of a shadow area and a layover area, so a dark area with a bright area. This is quite different to what it looks like in optical data. Like in this multispectral optical image, you can see that the looting hole actually is a fully dark spot. If you draw a cross section, the reflectance drops at the looting hole like that. If you draw a cross section across the radar data, you will see a drop and then a jump in the radar backscattering due to the coupling of these two signals. And here is what the site of Apamea looked like in October 2014. As you can see, these are the Justinian walls with the towers, and here you have all this land that is completely looted. You can recognize the different features and the different morphology of the excavated site compared to the unexcavated site. As you can see here, you have an example of a good looting mark, coupling the shadow with the layover due to the geometry of acquisition of the radar and depicting very, very clearly the looting pits. Here to the right, you can recognize the columns. You can even see the shadow of the different columns here and here, and you can see the top of the columns, the layover in here. So since the looting pits have this shape in radar data, you can describe mathematically the existence of these looting pits in the land by using this variable, this parameter, which is called texture. You don't need to care about this formula now because this formula is implemented in many GIS systems or many other software. So you can exploit the texture feature to extract information about the texture of your area of interest. And as you can see, every time you have a looted ground, the texture will be very high. Every time you have unlooted ground, you have a low texture. So you can reclassify the texture image and clearly map the looted sites as we did in Apamea. And here you see 3 different dates with the original SAR images at the top and the texture, the classified texture at the bottom. And you can recognize the appearance of new looted ground in the texture derived maps. And here the overview of the whole site. This is the mapping of the looted areas based on the texture. in October, with respect to March, there has been a 1% increase in the amount of looted ground within the archaeological site. So not much from March to October, but then clearly there was an increment that we will see in the next slides. Here, another detail overview of how the site looked like in Cosmos climate data at 1 meter resolution. Even with 1 meter resolution, we can see the difference between the looted ground and unlooted ground, especially in areas very close to the colonnade, but also in here, these heavily looted areas, they are all poach marked. So it's really a clearly identifiable parameter that you can use through the texture computation. And this is texture computation, again, with Cosmos Climate. You can see the looted ground with higher texture, unlooted with lower texture, and you can classify the texture again as we did with the TerraSAR-X data and identify new areas, newly looted areas like this one, delimited in cyan, matching perfectly with optical data. So, going back to the original scientific question, what about looting rates? So this is what we answered through the analysis of the ratio. I showed you the ratio when we looked at the case study of Nazca. This is another application of the ratio change detection. So we created the ratio between consecutive TerraSAR-X images acquired at the site every 2 months. And every time there was a signal indicating the appearance or disappearance of a looting pit, we track that and map that in our database. Clearly, we created an interpretation matrix. So when we compared the first image with the second image, we could have a number of cases like unlooted ground with similar patterns in the second image, new looting appearing with the appearance of a pit in the second image, hole filling when the material was the excavated material was put back within the hole to close the hole. We have a number of instances like that. So you have the hole in the first image, you have unlooted ground, even if rough, in the second one. If you have no change, you have the hole and the same hole in the other image, and you have a number of looting clusters in other cases. So if you implement these interpretation metrics, you can actually count the number of looting pits. And this is what we did based on the radar products. We counted the number of looting marks and filling marks appearing every 2 months to compute the number, the rates of looting. As you can see, in the worst periods, we reached up to more than 500 new holes from April to June 2015. So new holes excavated each month, clearly by hand, but also with the excavators, as I said before. So you can see the amount, but also the distribution of the looting pits based on this study. Of course, unfortunately, well, we continued the study and we saw that unfortunately the looting was still ongoing in 2019. As we can see in this Cosmos Climate derived product showing the ratio product and enhancing a number of new features very close to excavated areas at Apamea. So a last slide for this first part, a few considerations about using very high resolution SAR for looting detection. If you use spotlight mode, for instance, what we did in Cosmos Climate with Cosmos Climate constellation data, you can get information about surface disturbance and surface features linking with looting, like by computing, and you can get a flavor of newly looted areas or unlooted ground. If you go below 1 meter with steering spotlight mode, for instance, with TerraSAR-X data, like we did with the acquisition campaign, you can even go to the single looting pits. You can achieve very high temporal revisit, so very high temporal resolution. You can image the same site every a few weeks, every month, every 2 months, but also up to 1 day if you use constellations like Cosmos Comet. You can program some regular acquisitions, so regular tasking, and you can acquire night and day thanks to the capabilities of the radar. Of course, the data are not fully accessible sometimes, so there are announcements of opportunities like open calls for science applications that you can go through to get a number of free very high resolution SAR data like TerraSAR-X or also Cosmos Comet from the Italian Space Agency. But on the other side, you can also go commercial, so you can purchase some data with money through commercial loans. The last point, and this is in red, as you saw before, the use of this data for such applications requires a lot of expertise, especially for data processing and interpretation. So you need a training course like this one, you need a lot of practice, you need software development, a lot of experience to really become acquainted with the data. And this is probably why SAR is still in this domain, because it's not very user-friendly, but it can become so through training, as you saw today, I hope. So here I'm leaving you with a first very long list of references that you can access and refer to concerning these first case studies. Most of them are open access, others are not, but if you need a copy, you can send me an email to the address that you can see at the bottom of the slide, and I'm happy to send you any copies of any of these papers. So this is the end of part 1. So now if you have any questions, please feel free to ask them through the chat or through the microphone. I'm happy to answer them. I'll check the chat. No questions in the chat. Do you have any questions? You can open the microphone and speak. You can ask them in Spanish, as I said before, in English, in Italian. I can understand any of them.
Hi, Francesca. I actually have a question. Thanks for the presentation. It was very interesting. When it comes to post-processing of the images, such as like using the color codes for the different dates, or this last processing that you have done with the texture, has that been done like also with the Cosmo Sky tool, or like is that your own like which software has been used?
Okay, well, this is a good question. There is specialized software that you can use. I'm sure during the course you've heard about different tools, and some of them are free, some of them are commercial. But in general, you can even use the free software like Snap. I'm sure you've heard about Snap during the course. So you can process any of these SAR data with Snap. Then you can create GeoTIFFs that you can import in GIS. So you can compute the ratio in GIS. You can compute the color combinations in GIS. There are functions to do that in ArcGIS, I'm sure, in QGIS as well. In GIS, you cannot compute the coherence because it's an interferometric advanced processing that you can do in SNAP. But surely everything is doable with free software like SNAP or QGIS. Any of those, yeah.
Okay, thank you.
You're welcome. Anybody else? Well, I'm happy to answer them even via email or via chat if you have others later. If not, going through the program, the idea now is to have a short break, so we can take a break of. The plan was 10 minutes, but we are a bit late, so let's do 7 minutes, and we can be back at 11:12 or so, and start with part 2. See you in a bit. Okay, I think we can start again with part 2. I hope you had enough time to have a short break. Okay, let me open the slides again. And we go to the next group of case studies. So this group is all about Iraq, because this is unfortunately a very interesting site, scientifically speaking, for a number of applications involving SAR data. The first one will be about remote sensing of archaeological mounds. So archaeological mounds, or also in Arabic tells, are topographic features of different spatial dimension and shape that have been created by either the humans or geology by depositing an amount of materials over several years or even centuries. And they have often an archaeological potential, meaning that they have been used as burial mounds or tumuli, so to create tombs and within, or also to create urbanized lands on top of them, like used as fortifications. So the state of the art in the use of remote sensing for archaeological mounds sees different levels of detail depending on the resolution of the data that is available to date. Here a few examples. The example called A by Menze and other authors in 2006. They've used the NASA 90-meter resolution SRTM digital surface model to map archaeological mounds on a supra-regional scale, meaning that they could only identify big ones, the very huge ones that could be actually seen with 90-meter resolution data. Nikulita in 2020 used LiDAR data at very high resolution in figure B at the bottom right of the slide for the geomorphological study and recognition of the burial mounds, and a semi-automatic approach to map these mounds using a GIS software based on the LiDAR very high resolution data. Other authors, Berganzo-Berga et al. In 2021 used a combination of LiDAR and multispectral optical data for large-scale automatic detection. So a number of authors have used digital elevation models, either at low or medium or high resolution, very high resolution, or optical data. But there was very, very limited information about the use of SAR and related products for archaeological mounds detection and mapping. So we did this study in central and southern Iraq, looking at this area that is called mainly Wazit. This area has witnessed for millennia the rise and decline of many famous civilizations like Mesopotamia and Arabic civilizations between and across the Tigris and Euphrates river plain. So everybody studies them at least at school in Europe. So it's a famous area in the Middle East. So what we did is to use this area as a demonstration case study to verify the capabilities of InSAR derived digital elevation models to detect and database archaeological tales from space. The first dataset is indeed SAR-derived digital elevation model. In particular, we use Cosmos SkyMed data, a 3-meter resolution in the strip map mode, to derive DMs, digital elevation models, at a final resolution of 10 meters. So these are on-demand tailored products from the mission. So the Cosmos SkyMed mission usually acquires data and processes single images, but if you make a particular application to the Italian Space Agency, you can ask them to process some digital elevation models for you, to acquire data and process digital elevation models for you, or you can also take the original images and create digital elevation models yourself with mainly 2 techniques. One is interferometry, and the other one is radar grammetry. So in this case, in particular, we used radar interferometry to create a DM at 10 resolution. And as you can see in the images to the right, here we compare the same area as seen in the digital elevation model derived from Cosmos SkyMed and the elevation model derived from ALOS global model at 30-meter resolution. So from 30-meter resolution to 10-meter resolution, you can see an amazing change in the capabilities of elevation models to identify mounts. The other data set that we use is an optical derived surface model, and this is called Cartosat Euro 3D model. It's derived from using photogrammetry from chromatic optical images acquired from this Indian mission in 2015, 2019. This is generally available everywhere, but the goodness, the quality of the digital elevation model depends on the amount of satellite images used to create the model. So in red, you have the indication of the zones with the highest quality, and then you have good quality in the orange ones, and yellow the lower quality but generally available models. And this is the status in 2016. So today the status is clearly improved compared to the overview that was provided in 2016. So here the view of the same area at 5-meter resolution with this model, as you can see, compared to the Cosmos SkyMed DM, this is a bit coarser, but the resolution is much improved compared to Cosmos SkyMed. We will see some details about the quality and capabilities of digital elevation models in these next slides. First of all, how to identify, geometrically speaking, the archaeological tells. So we developed this simple model in 2D and then in also the vertical cross-section to identify the key geometrical features of the archaeological tells. First of all, the perimeter, the area of the base of the tell, then an index quantifying the circularity of the tell. So the closer to one, the closer the shape of the tell is to a circle. The planar shape, like classification in circular, elliptical, irregular. The maximum diameter, the ferret diameters, which are official geometrical quantities that you can also extract in GIS with specific scripts based on the data. And then in 3D, talking about the 3D shape of the digital surface model, the elevation of the base, the elevation of the top of the archaeological tell and the difference between these two quantities identified with the capital H and basically identifying the height of the archaeological tell. And then last but not least, the volume of material involved in this mound. So first of all, how these tells look like in satellite data. So this is a very high resolution base map from ArcGIS. Here in the first map, you can see the satellite view of the tell in the optical data. This is the more or less the boundary of the site. If you use multispectral data and a band combination involving near-infrared, red and green bands, this is what you see from space. If you look at the SAR data of the tell, you can see its signal a bit distinguished from the rest of the scene due to the difference in material and surface roughness of the archaeological tell. But the most important difference comes up when you look at the digital elevation model like the Cosmos SkyMed DM, in this case, which is showing you clearly the elevation of this mound, and you can recognize the shape, the planar shape of this feature. You can draw cross section, you can clearly understand the morphology of this tell. This is a case of so-called preserved tells, so without any particular and specific human disturbance. This is another example of disturbed tell, where a number of human actions and landscape changes and modifications occurred through the years. Again, to the left, we see the satellite view of the tell in very high resolution base maps. You cannot recognize much, actually. Here you can see the false color combination of the multispectral data, Sentinel-2. And here in the third one, you can see the Cosmos SkyMed strip map data, 3-meter resolution. You cannot see much, but when you look at the digital elevation model, clearly you have signs of the presence of this tell, even if the shape and the morphology is a bit disturbed with respect to other sites. This Neo-Babylonian tell, it's clearly still there, clearly recognizable in the DM product derived using InSAR. So what we did was to use this digital elevation model to create a database of all the visible archaeological tells in the study area. And together with the archaeologists, we could classify, first of all, the archaeological priority of the site, giving the level of archaeological signals and archaeological potential of the site, because we could see some features suggesting the presence of archaeological ruins or the archaeological value of the mound. And then we also classify the archaeological tells based on the presence or absence of looting features. So here you see the distribution, the spatial distribution of these classifications. And as you can see, there are clusters of looted sites in several sectors of the study area. We also made statistics and everything, like more details about that are all accessible in the open access papers that you can consult for more details. Something very interesting that we did was to compare our digital elevation models with military aerial photographs from Corona. So we are talking about images from the 70s, the 60s, the 80s, depending on the military mission. The United States are progressively releasing a number of these photographs for many countries in the world. So if you are lucky, you could have some free historical photographs from these missions that are helping you to do archaeological studies. Then we also use Sentinel data, multispectral data. And here is an overview of the optical derived Cartosat DM that I showed you before, so the 5-meter resolution one of the same area of interest. But the important and interesting part is how to derive further products, so other levels of derived products helping us with interpretation. This was done in GIS, so free software again that you can use based on a digital elevation model. And these are two typical morphometric indices that you can derive based on the digital elevation models. One is called the topographic position index, and is basically the difference in the elevation at that location with respect to the average elevation within the neighborhood of the pixel, and the deviation quantifies the amount of difference with respect to the mean elevation of the surrounding of the pixel. So they basically are indices enhancing the presence of a mound with respect to the surrounding terrain. So every time you have a mound, you can actually see the mound better by using this index with respect to the conventional displaying approach of a DM. So if you compare map C with map D, you clearly see what I mean. So the mounds in the topographic position index appear as very bluish spots, and the remaining land, the surrounding land, tends to green and yellow because it's more flat compared to the mounds. Then you can also compute this DEV, deviation from mean elevation, and try to understand how much these mounds deviate from the surrounding morphology, and based on that you can do morphological classification in stream, drainage, or upper slope, high ridge, hilltops, depending on how this index comes up within your analysis. This is really interesting, quite innovative if you use high resolution data, but it's very much used in morphometric analysis of topographic features and landscapes, also in geomorphological studies to create geomorphological and geological maps. So by using the InSAR derived DM, the optical derived DM, and the historical maps, what we could do is to create an enhanced, updated database of archaeological tells within this region. By considering only the portion of the region for which we analyze the Cartosat DM, we can see that the total of mapped tells is 344, so it's 10 times more than existing databases, like the database identified with stars, the Ancient Near East database. And clearly there's a spatial pattern that you can recognize. For instance, a number of tells are aligned along current or ancient river or channel plains. So there is a study in terms of archaeology and paleolandscapes that can be done considering this distribution. There is a variety in terms of shapes. Many tells are irregular as of today, or as up to the most updated information that we have about them. And now I'll tell you a bit more in the next slides. Some of them are elliptical, some of them are circular. But the evidence is that they are many more than they were by simply looking at optical data. So what we did is also to study the accuracy and the goodness of these products, both against each other in one plot. And as you can see in the first plot, the optical derived and SAR derived DMs are very similar. So the differences between them, pixel by pixel, are mostly concentrated around zero difference. So they match really well. And if we compare the height, the elevation of all the different tells in the optical derived, the radar derived, and the two external DMs at a lower resolution, we see that there's a match in the distribution of these elevations, especially between the InSAR derived DM based on Cosmos climate data and the ALOS product. And when I say small differences, this is what I mean. We are talking about 1 meter, 1.5 meters difference. If you think about the general accuracy, vertical accuracy of digital elevation models, this is a very, 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 very good quality for these radar-derived surface models. So it's really an opportunity for these studies. Something else very interesting that we studied is the relationship between some parameters of the mapped tells and their possible use to derive additional information. So here, first for Cartosat and then for Cosmos SkyMed, we compare the area of the DM with the height. Then we compare the volume with the height and the volume with the area of each tell. What we see is that there is a clear relationship between the different parameters, and the most striking relationship is between the area of the archaeological mound, so the planar area, and the volume. And actually from these evidence plots, we can extract even a formula telling us how much is the volume if I know the area of the archaeological tell. This is not generally valid, and what I mean is that it's very site specific, so you cannot use this formula that was derived for Wazit in Iraq to gather informations about tells, I don't know, in Africa, but it's a specific, but it's really important because it allows us to understand the potential volume of a tell that we don't have information about at the moment. For instance, we had a tell that was visible in the historical data, like the military corona datasets, but then the tell was destroyed to create space for agriculture or to build, I don't know, a village, a town. So we don't have elevation information at the moment. There's no way we can compute the volume, but with these sort of plots, if we know the planar shape, we know the area. And once we know the area, we know with a little bit of approximation, the amount of cubic meters of material involved in that particular archaeological mound. Obviously, this is something related with what I said before. There are a lot of anthropogenic impacts that are visible when studying archaeological tales from space and combining all these archaeological all archaeological evidence with satellite information. In many sites, we have anthropogenic interference. For instance, in this case, there is a clear cut through the archaeological tell occurred to build a channel or in other cases a road, and part of the tell was totally flattened to create space for agriculture. So that's a process that unfortunately is very, very common. In some cases, we also see looting, like in this case, you can see the looting pits at the top of this mound. So we studied this sort of evidence in the database to try to map the spatial distribution of the different impacts and threats due to anthropogenic actions. So starting from the top, we have in red the tells where we detected reworking and reshaping of the planar shape of the tell. In brown, we have those tells that were leveled or flattened, so the topography was totally destroyed and the land is now flat. We have the evidence of looting in green. We have impacts from agriculture in blue, building construction in pink, fires in some cases in yellow, modern canals in cyan, construction of roads in black, disturbance by heavy vehicles, so heavy vehicles crossing the tells in darker yellow, and in violet we have a change of use. For instance, on some tells we detected new buildings on top of the tells, so the ancient mounds were recycled, reused for more modern uses. But in 36% of the cases, tells that were found as reworked or reshaped. For them, we also observed that the former morphology and shape were totally changed with respect to the past, and they were also looted. So the different threats are also interconnected. Here, the example I mentioned before, a few tells that you can see in the ancient military data and that are now totally invisible to more modern satellite acquisition. So here the value of the old data, but also the value of relationships between the different parameters like area and volume that I showed you before, because this is the only way for us to understand the volume of those sites in absence of any other topographic information from current models. So to conclude this particular application in this site, opportunities. So both these digital elevation models are available for many locations in the world. So Cartosat can be accessed to through announcements of opportunities through the European Space Agency. Of course, they will provide you with a limited amount of square kilometers, but it's enough for a specific archaeological site or region that you can want to investigate. The same for Cosmos SkyMed. You can apply for free data through the announcement of opportunity, the open call for science from the Italian Space Agency, and you can apply for the generation of high-resolution digital elevation models that they can create for you, or you can create the digital elevation models if you're happy to go through advanced InSAR processing to create the models. Both these DMs proved reliable and also suitable to investigate archaeological tells if they have an elevation of a few meters sticking from the surrounding landscape through the use of morphologic and morphometric indices. And we demonstrated that an inventory of archaeological tells can, based on these products, can reach up to 1 order of magnitude more identified features than conventional methods. So here are opportunities to take into account if you want to follow this scientific route. Obviously, the most important limitation is, and also idea for a follow-on, is about the doubt about the interpretation. So what we see here is a mound, but from space it's sometimes very difficult to understand whether it's only a topographic relief due to a combination of weather and meteorological and morphological events creating these mounds, for instance, along riverbeds, or if there is an anthropogenic and archaeological potential. So we need archaeological information, archaeological details, and an interpretation by an archaeologist to understand whether or not this particular tell is really an archaeological tell or a burial mound or simply a geomorphometric feature. Clearly, we need in situ observations and validations to constrain the interpretation. The fourth case study is actually including the previous one. It's a wider region in Iraq, including Wazit, so the Tigris and Euphrates river plains, but a much wider area from the north of the capital Baghdad up to the south to Basra, up to Saudi Arabia and Iran and here at the southeast. This is a very wide region full of archaeological features, archaeological assets. In particular of interest here in the map, I've plotted the chain of so-called Abu Gir springs. They are a number of ancient springs, so water supply points that were used by the civilizations as main sources of water for cultivation and for subsistence, and they are still used today in many cases. So many of these springs are still active. Many other places like forts and farms and ancient canal systems and ancient traditional cultivation systems are available in this region, most of them linking with Sasanian origin. The area includes the Wazit Governorate, which is here, the one we've been imaging before with digital elevation models, and also the sites of Basra here, and Eridu here, with ancient canals and water networks dating back to the 2nd millennium before Christ. This is a very important area because it's within a country that has been classified unfortunately, in the top list for the most climate change impact affected countries in the world. So the heritage, the archaeological heritage, but the heritage more broadly speaking in this region is heavily affected by both natural climate related processes like dust storms, droughts, changes in temperatures, changes in precipitations, in addition to human-related factors involving, for example, the modern development, changes in agricultural patterns, development of new agricultural fields, in addition to archaeological looting, again, and a number of other cascading hazards like pollution, fires, destruction, and so on. So, and a highly impacted region, but a very good scientific testbed to use satellite data. And this is what we did for 3 main purposes. In this region, the first goal was to do archaeological mapping, and we did that with very high resolution declassified images from the US Hexagon mission, recently declassified and available openly from USGS. We also use medium resolution to very high resolution optical InSAR data like PlanetScope, Landsat, Cosmoscan, and Spotlight, and Google Earth and other base maps available for free in GIS. The second objective was to do multi-temporal change detection, and we did that both with radar and optical. And with radar in particular, I'll show you in the next slides, we use Sentinel-1 data and change detection through interferometric coherence. And then we did multispectral change detection with Sentinel-2. And last but not least, the third objective was to study impacted areas at regional and country scale. And we did that using Sentinel-3 data at 300-meter resolution. So you understand it's a regional or country-wide assessment to study dust storms occurred over the last years. So the main digital outputs are archaeological sites and ancient water systems delimited, like mapping of canals, water bodies, and ancient springs, and also derived products of change detection, like change maps, and then in the next steps, we will also produce maps of endangered sites and susceptible regional susceptibility maps. So let's see a bit some details about the heritage of this region. So this is a zoom very close to an ancient branch of the Euphrates River. So you can see the modern Euphrates in the north, and then the relict Euphrates branch in the south. And all you can see in green is a network of historical and 20th century canals. So here, basically, this is like a zoom onto a map where we of an area where we recognize a sequence of canal constructions, a sequence in time of canal constructions and reuse and recycling and abandonment. So many canals which are depicted in pink are those extracting from the ancient Euphrates River, and they dried up around in the first millennium before Christ. Then we have in green historical and 20th centuries canal abstracting from either the modern Euphrates River and the springs. And also we have a set of unknown canals that we are still uncertain on how to classify, because we need more fieldwork and insight evidence to deepen our analysis. But what's important here to see is that all these features are clearly depicted in the satellite data. This is a keyhole image from 1981, so it's an optical photograph which has been orthorectified and georeferenced, and here you can see all these features very clearly. Especially these depicted in pink are sinuous ancient canals that are now partly reused by modern canals. This is the original image, so you can see the details are in the images, so it's not only an overlapping of other lines and sources, so they are really, really clearly detected by the satellite image. And last but not least, they are really easily recognizable even in modern data. So Cosmos Climate data acquired last year or 1 year ago. Even if we don't see actually the lines at surface. With the radar, we can see the traces of the ancient canals in the radar signal. So this is a Cosmos climate at 1 meter resolution, and here it's an amplitude, so it's radar backscattering, showing you the differences in soil moisture at the surface, and also there is some penetration of shallow layers. So what you can see is very clearly the network of the sinuous lines of the ancient canal. So that was about the archaeological mapping, a few slides about the archaeological mapping. Now we move to the change detection. So this is based on coherence, InSAR coherence. It was done using Sentinel-1 data, exploiting the interferometric wide swath mode, and in particular the VV polarization. We decided to use a number of yearly pairs, looking at consecutive years, and we use the method of differential interferometry by exploiting the processing platform of Alaska Satellite Facility, available to anyone if you're interested. And the output for from each processing was a coherence map, among other layers. We had coherence maps at 40 meter resolution. So in this example, as you can see, in black, you have loss of coherence. In white, you have a coherent side, so no change, and in white and change in black. In black, in particular, here we see a number of newly irrigated fields, and we will see them in the next slides in much more detail. So here the overview of the regional scale processing with the yearly pairs starting from 2014 and up to 2023. Based on coherence, as you can see, whilst the Western Desert is generally coherent, there's a lot of change in the river plains and also at the margins of the river plains, as we will see in much more detail later. So here is the overview of the ancient springs of the Abu Gir, color-coded according to the yearly coherence at each annual pair. And here is the overview of the overall average yearly change at all these springs in the whole period 2014-2023. As you can see, you can recognize two different clusters of springs to the north, so-called northern cluster between the Tartar and Rizaza Lake. We have a mixed component of uncoherent, so decorrelated and correlated scenarios around the springs, whilst to the south, the southern cluster is very much decorrelated with a lot of springs represented in orange, dark orange, and also a number of ancient tells and sites depicted in orange, meaning that the correlation was much stronger. So to investigate this decorrelation a bit into more details, we implemented a change detection workflow based on optical data, Sentinel-2 in particular, so free data with Google Earth Engine. And we developed this code, which, by the way, is freely available. If you want to get a copy and study your region of interest with the code, you can use this link available in the slide to access the code and reuse it for your studies. And this code basically automatically gets the Sentinel-2 optical data from Google Earth Engine and create the yearly composites, creates vegetation indices like NDVI, and then through some thresholding and some further post-processing routines, extracts derived maps and parameters, both in terms of maps, like NDVI maps, NDVI difference maps, but also at points of interest. For instance, what we did was to extract values at the ancient springs by inputting the coordinates of the springs. So this is an example of a change map based on an NDVI difference. Every time there is a difference depicted in orange, like these circles, it's due to the occurrence of changes due to new agricultural fields irrigated with the so-called center pivot irrigation system. So it's a rotating a branch irrigating the site circularly. And so what you see is a change in moisture and change in vegetation. Every time this change is close to our archaeological sites or heritage sites, clearly there's an impact, there's an issue. So here is simply a sequence of the vegetation index and how the vegetation index was changing throughout the years. You've seen a lot of change, which is all now quantified through the NDVI change maps, all created through this code that we developed. And you can see a lot of change, especially at the lakes, because some of them, like the Sawa Lake or other lakes like Hamar, they are progressively drying out, or in some cases they are drying and then watering again. But also you can see a lot of change to the south of to the bottom of this figure, the circular shapes that I mentioned before, these agricultural fields, so also changes at the agricultural fields in here. There is a lot of development of new agricultural fields, sometimes very close to the ancient springs, and some of them have been impacted. This is another product that is created by this code. It's the change magnitude, and basically it's telling us the amount of change, accounting also for all the different bands of the multispectral data. So whilst NDVI was only accounting for the near infrared and red, here we combine the values of all the bands, so we can detect more changes. And this is the overview of the detected changes, the proportion of changed sites with respect to the unchanged sites at each yearly pair. And as you can see, there is a difference when you account only for the NDVI change and compared with the change magnitude approach involving also soil moisture changes that are depicted in these red bars, for instance, due to changes in precipitation or changes in soil moisture during that particular date, or also plowing of agricultural fields, so movimentation of soil that is clearly changing the reflectance of the terrain in the satellite image. Other changes at the local scale, again, we are talking about looting, unfortunately, and here are incidents of looting damage that we could depict with the Cosmos climate data at 1 meter resolution. As you can see, the looting pits are here clearly depicted with the brighter zones in the data, and the increase in the texture of the data where there is looted ground. And here an example of canal construction and flattening that we could also see through the combined use of historical photographs, more modern, very high resolution Google Earth data, and Cosmos climate average amplitude images, like in this case, when this archaeological tile is clearly cut through a canal, a modern canal system. So it's the impact of this construction, and also some tire marks of cars passing by and other canal systems are clearly visible in the data. So to conclude this fourth case study, in these maps, we've seen how Sentinel-1 and 2 data can help us to extract important information and insights into landscape changes at the regional scale and the potential impacts of a number of natural and anthropogenic processes to heritage assets, in this case, the springs or the archaeological tells and other sites. We can also map disappearance and modifications to agricultural lands, but also natural reserves like water bodies, like the Sawa Lake that was often in the media in the last few years. Now we are continuing our on-site in-depth analysis at the local scale to better constrain the causes for the detected change and to understand whether it's confirmed to be a natural or anthropogenic impact. And we are continuing the monitoring with Cosmos Climate at 1 meter resolution, a campaign that we launched in 2023 and it's still ongoing. And in collaboration with UNOSAT, we are also combining these with interpretation of very high resolution commercial data from Maxar, worldview data, to compare and evaluate the usefulness of this imagery for archaeological studies and impact assessment and landscape studies in this region. And again, for these two case studies, I leave you with 5 references. In this case, all of them are open access. So if you are interested in any of these studies, you can find all the details within these presentations. Also, these papers. The last one in particular is led by only the Iraqi stakeholders. So that one is more focused on the archaeological value of the region, whilst the other one are also involved, well, mostly involve the technical assessment of the satellite products and the satellite methodology. So depending on what you are looking for, you can access the different studies. So I'm happy to take any questions now. I don't know if you're still there, if you survived, or if you are too tired. So please tell me if you have questions, if you want to speak with the microphone or type them in the chat. I'm happy either way. Okay, here I see a question. Really interesting, thank you. You're welcome. Sorry, I can't turn on the microphone. Oh, you are in the office, no problem. These datasets you have generated showing the risk of looting to which archaeological sites are exposed. Have they been taken into account by the authorities? Have they any impact on heritage conservation policies? Okay, yes, we are trying to engage with the archaeologists and authorities of the region. In this particular case, it's quite difficult because we are talking about Iraq. So let me say that the community, the government is more open to listening to specialists from their countries than from other countries. So what we are doing is to work in strong collaboration with the Iraqi stakeholders, in particular Professor Jafar Joteri from the University of Al-Qadisiyah, and is our local champion, let me say. So every time we produce some satellite maps and satellite products within this collaboration, he tries to disseminate and show these products and derived maps to the authorities to make them aware. It's a difficult process because, you know, here we are talking about human impact, but also climate change. So there is a lot involved in the decision process, and but yes, we are doing that to the best level as we can. I hope I answered your question, Sonia. Anybody else? Okay, thank you. Yes, you're welcome. So, yes, so if there are no other questions, we can have another short break. I planned 10 minutes, maybe we can do another 7 now, and we can meet again at 12:15. So 12:15. See you in a bit. Okay, here we are again. I hope you had a nice break. We now start with the third and last part, and then we break definitely for lunch, I think. So let's start with this last one. This is a bit different from the other ones because it's fully focusing on the use of multitemporal InSAR for heritage-related applications. So just to recap, and so you had a long time to analyze and discuss these methods. We are talking about advanced multitemporal methods, processing a number of SAR images with these so-called interferometric methods, allowing to identify and track a number of persistent or permanent scatters or coherent targets, and track their position and any displacement through time in relation to the time coverage offered by the satellite data that were used as inputs. As you know, the output of such processing approaches are databases of point-wise targets with associated annual velocity, average coherence, and other coordinate information to locate them, like height, but also displacement time series. So each of these points is associated with a time series showing its displacement history with up to 1 millimeter precision through time. So you've been talking, I'm sure, about persistent scatterers methods and small baseline subset methods. These are similar techniques in terms of the family of multitemporal InSAR techniques, and they work every time on the ground you have a target or a landscape acting as a persistent or coherent reflector to the satellite signal. So, for instance, when in this part we are focusing mainly on urban areas. So, if you have a house, a building, a rooftop, or if you have a reflecting metallic object, all of them are easily identifiable as a persistent scatterer or coherent point. But if you have vegetated areas or water areas, these clearly cannot be are not suitable to provide you with measurement points after the advanced InSAR processing. So let's dive a bit into the applications of these methods into heritage sites. Here we have an example of a retaining wall, which is imaged as a persistent scatterer by this type of technique. To the left, we have the first date, so when the wall is at its original position. After a certain time, the wall sinks a bit due to geological reasons. So what you see with these multitemporal InSAR methods is the amount of displacement that the wall has been affected by, projected along the satellite line of sight. So this delta D that is represented in this simplified scheme. When we look at more complex sites, we can have displacements like the one I've showed you before of this wall. We can have local collapses of surface landscapes due to underground structures, like in this case. You can have retaining walls of archaeological sites, of heritage sites that are tilting. So in each of these circumstances, you will see probably a signal, you will probably detect a PS, but as you can understand, the information of the signal that you see from the satellite is the most tricky part because you need to account for a number of factors and a number of geometrical reasons causing that particular motion. So the use of these methods in heritage sites, in particular UNESCO sites, UNESCO World Heritage sites across the globe, has been increasing since the year 2000, more or less. At first, the most exploited sensors were clearly those from the first generation, so ERS, MVSAT, so those missions that were launched in the 90s and at the beginning of the 2000s. Then, starting in 2007, we had a progressive start and increase in the use of the second generation satellites due to the launch of Cosmos Skymed, TerraSAR-X, but also RadarSat-2. And then in 2014, some application with Sentinel-1 started. And clearly, these plots and graphs are continuously increasing because we are witnessing a boost in the use of InSAR methods in heritage sites. And the value of space radar is obviously now recognized by the scientific community, but also by the general public. I was interviewed in 2016 by a reporter by BBC because I was coordinating a project on the use of satellite InSAR for heritage sites in Europe. And immediately when they've got the news of this project, they wanted to talk about this application to the wider public and in the science news. So even the media understand the importance of this data and the value of this data and this type of research and application in heritage sites. So the first case study that I will show you in this group, in this third and last part of my presentation of this module, is what we did in Central Mexico. So originally the application was not done just looking at heritage, but obviously the target is much broader. It's the whole city of Mexico and Mexico City and other cities in Mexico as a town, as a metropolitan area. But of course, within these metropolitan areas, there are a number of heritage assets like churches, the cathedral, and other ancient buildings and roads that are classified as heritage assets. So everything we will see in this presentation is a bit broader, but includes obviously cultural heritage targets within it. So in this particular case, we are talking about impacts of a natural phenomenon that is anthropogenically influenced. So we are talking about land subsidence. I'm sure you have heard about this process in the previous modules. In this case, in central Mexico, this is mostly due to overexploitation of groundwater resources and the decline of groundwater levels and compaction of the underground aquifer system, and in particular the clay layers. This process has, as you can see in the animation, significant impacts on the surface. So you not only have a loss of volume in the underground, but obviously at the surface you have a lot of consequences. One of them is tilting and on-level sinking, like as you can see in these undulating roof lines in Mexico City in the photo at the top. You have a number of fissures and cracks in private buildings, but also all the ancient buildings, like in this one. Other apparent damage is along the transport network. You have a number of cracks and jumps in several regional but also local roads due to differential sinking of the surface. As I said before, a number of historical and religious buildings are involved. In Mexico City, the most affected one is Mexico City Cathedral. As you can see in the photos to the left, the cathedral is being impacted by this process in terms of tilting due to differential sinking, but also a lot of cracks have been recognized in the wall, external walls, and other landmarks across the city have been impacted. Like in here, you have the Ángel de la Independencia, and this is a statue that was built many decades ago, as you can see at the beginning of the 20th century, in 1910. This is this is similar to the original layout of this statue and this column. As you can see here, a few decades later, due to the subsidence of the surrounding terrain, they had to build additional steps to reach the monument because the ground was sinking, but the column had very deep foundation, so it wasn't sinking. And due to the sinking, it started to uplift. It's not an uplift clearly, but it's a seeming uplift due to the sinking of the ground surface. So they had to build additional stairs. These are examples across the city. Again, in Mexico City, this is not a simple lamp post or a pile, but actually it was a water well. It was built at the surface level, but then after several years of subsidence, all the ground surrounding the water well subsided by 8 meters almost. And then the well, since the well was founded very deeply underground, it didn't sink with the ground, and it's now sticking out the ground by 8 meters, as you can see in the photo. So these are examples of other cities in central Mexico. As you can see, this wasn't originally part of the layout of the city. This is a step due to subsidence. This is a step due to subsidence of the road. This was the garage. Of course, it was at surface level before. Now it's not accessible by car due to the sinking. So you can understand the amount of impacts, and also the impacts in terms of in the housing market. As you can see here, many houses and lands are not suitable anymore to be sold, and so it's an important impact across these cities due to this process. So what we did is to use Sentinel-1 images in the whole central Mexico to run a quasi-continental InSAR study of land subsidence in this region. And we used the parallel small baseline subset workflow developed by our colleagues at the Instituto of CNR. This is implemented in the geohazard exploitation platform of the European Space Agency, and it was done freely through a sponsorship project sponsored by ISA. And so this is an opportunity that you can also consider for your future studies. And what we did, we processed 1,700 scenes covering 2 years of acquisitions, 2019-2020. And we then combined, we merged all the different results into a quasi-continental product. A number of subsidence hotspots were identified, like Mexico City, Aguascalientes in the other zoom, and many others, some of which will be analyzed more in detail in the next slide. And in addition to processing, we also carried out an important other activity, which is validation. So we estimated the accuracy of the InSAR-derived displacement velocity against independent geodetic monitoring through leveling and GPS carried out by the National Institute of Statistics, Geography and Informatics of Mexico, INEGI. And this was a work in collaboration with them to compare what we could see from the satellite against global position systems and leveling traditional geodetic monitoring stations. And here, as you can see, the errors in the standard, in the estimations of velocities along the vertical directions are typically lower than 20%, even for locations that are subsiding more than 15 millimeters per year, which I can tell you in terms of accuracy, it's really high considering the amount of data that you can get out of such a processing exercise. So the first case is the hotspot of Mexico City. I'll go through 3 hotspots. This is the biggest one. It's the capital. It's basically the federal district, and broadly speaking, we are looking at the metropolitan area of Mexico City. So it's even more. It's bigger. It's bigger than the federal district, and this hotspot of subsidence is clearly linking with the distribution of the lacustrine deposits. So the compressible clay and silt deposits that formed when the ancient lakes, among which Texcoco, were dried out to build the city. So we are talking about ancient times, but still the effect of these drying out of sediments is still visible, because the lacustrine deposits act as the aquitard of this aquifer system. So they are at the top of the system, but since people are pumping water out of the aquifer layer, so below these clays, as an effect, there is a volume loss and a volume change, and all this area in red and orange and yellow is sinking. It's not all sinking at the same rates, but the rates are strictly connected with the thickness of these clay deposits by some formulas that you don't need to worry about now. What's really important to see is that this is a 3D view of the same area. What's really important to see is that the soft compressible quaternary clay is sinking a lot. So it's the area in orange and red, whilst the areas in green are those from the hard volcanic rocks. These are not sinking, and in between you have the yellow zones, so-called transition zone, where you have slope deposits of sand mixed with silts and clay, and they are subsiding somehow. But what's important to see is that there is a sharp change in the subsidence velocities and the total subsidence. So here, this is not topography, but it's a map of the total subsidence in this period, displayed as it was a surface model. So the deeper the surface, the higher the value of the subsidence that occurred during those years. So what happens is that in the transition zones, you have a sharp difference in space between the subsidence in one location to the location nearby. So every time you have this differential sinking, this is where we observed that more cracks and damages develop on the surface buildings and roads and transport network. This is because any differential settlement basically induces the so-called angular distortion. This is a geotechnical quantity which is telling us the amount of settlement occurring between 2 points at a certain distance. So the higher the angular distortion, the higher is the probability that some damage will occur. Why are we looking at this? Because this is a suggestion for us on how to create hazard, subsidence-induced hazard products and hazard maps, and then in turn risk maps. So this is what we did for Mexico City for the first time in 2020 and published in 2021. So we consider the risk assessment formula, the general risk assessment formula in geological hazard studies. Risk is a combination of hazard, exposure, and vulnerability. So hazard information is telling us about how probable it is for a certain phenomenon to happen in a certain area with a certain magnitude. So this is a probability, and the elements at risk are then characterized by exposure and vulnerability. So the value and the type of assets that could be affected, and the likelihood for those assets to be damaged when they are exposed to that particular phenomenon. So if you take this into account, you can develop even if qualitative, but an assessment of risk induced by differential deformation. This is what we did in Mexico City. So we consider, as you can see in the map, the total subsidence. Then we created a map of the angular distortion, so the geotechnical quantity. I told you before, every time this quantity was high, we classify the urban blocks darker and combine this information with the distribution of the properties in each geostatistical area available from the National Authority of Statistics of Mexico. If you combine this information using the so-called risk metrics, you can basically intersect information about hazards, about probability, with the elements at risk. So for instance, the amount of properties per square kilometer. This is what we did by identifying a number of combinations where by more exposed and vulnerable areas when affected by higher angular distortions were classified as at higher risk level. As you can see, the output can be a map of urban blocks classified according to risk, meaning that red ones, so are for very high, so classified very high at very high risk, are the most likely where zones where surface cracks and surface fissures will develop in the buildings. Whether, well, either housing, but also they could be churches, monuments, and any other heritage, cultural heritage properties in that particular area. In particular, for this area, we estimated that, for instance, more than 300,000 properties were at high or very high risk in the federal district, and more than 450,000 were at the same level of risk within the wider metropolitan area. So the second hotspot, without going into detail about the geology or the hotspot itself, but I'm using it because I want to show you the difference in the spatial granularity that you can achieve when you develop these risk assessment workflows, depending on the data and the resolution of the element of information on the elements at risk that you actually have. So in this slide, we have applied the same approach of risk assessment intersecting angular distortion information with information about properties, the amount of properties per square kilometer. We've done that first at the scale of urban blocks, like broader urban blocks, the so-called AGEBs. In Mexico, they are homogeneous geostatistical areas. They can involve actually more than one urban blocks. And then we did the same risk assessment at the scale of single urban block or single building, because the database of buildings was available at that scale. And as you can see, if you have such a level of resolution, such a level of detail, you can refine your assessment, your risk assessment for your specific area of interest, and implement the risk assessment methodology up to the local scale using such an approach. So the output map will tell you the location of areas where is more likely that fractures and damages will develop in the buildings, in the structures, in monuments, churches, cathedrals of those particular areas of interest. The third hotspot is Aguascalientes, again in central Mexico. But the aim of this case study is to show you that we are not supposed to look at subsidence only, so the vertical displacement, but if available and if present, we should also account for the east-west displacement. So in this case, this is a valley, a full valley stretched north-south, where subsidence occurs, but also there is a lot of lateral displacement towards the center of the valley, and this is inducing the so-called hogging and sagging process in geotechnical engineering. So it's the presence of horizontal stress due to a sharp difference in horizontal displacements at short distances. I'm showing you this one because this is a typical information that you also have from freely available databases like the European Ground Motion Service. So you can actually account for east-west displacement data for any of the European locations of your interest. So we should account for these horizontal stress as well when we do our risk assessment analysis. And this is what we did in this case in Aguascalientes. So we implemented the risk assessment metrics, but also we accounted for the horizontal strain by increasing the risk by one level every time the horizontal strain exceeded a certain geotechnical threshold that we identified from the literature. So in this way, we could better account for the peculiar role of horizontal stress in the potential risk of structural damage to our properties within the city. So these sort of risk maps and risk assessments are very valuable, not only to constrain the deformation process in terms of saying which areas are subsiding and which are subsiding more and so on, but they are helpful to prioritize checks and detailed, careful monitoring and field inspections, because where this differential motion occurs is where risk is at the top. And when more accurate and higher resolution data are available, the assessment can be improved up to the local scale, up to building scale, and the improvement can be done also in terms of hazard information. So you can improve the elements at risk information depending on the database of buildings, but you can also improve the input hazard information by improving the resolution of InSAR processing databases by using, for instance, very high resolution data from TerraSAR-X or Cosmo, and also processing with advanced InSAR workflows to reach the single property scale. So, building upon our experiences in Mexico, and this is the last one that I will show you, we implemented a national risk assessment due to differential land subsidence in Italy. Why Italy? Not just because we are based in Italy, but because this is a country full of land subsidence hotspots. The capital city in Rome is subsiding, and a number of other river plains like the Po Plain, the Firenze Prato Pistoia Plain, the Volturno Plain, and many other locations across the country. So this is the ideal territory where to test these methodologies. And we did these tests within this sub-risk project that I'm coordinating since 2023. This is funded by the Ministry of University and Research of Italy. And all information about this project is available in the website that you can access through this link, through the slides, or also you can follow the project in Twitter if you have an account to gather news and information about it. So the project is working at different scales, but all have a similar goal of estimating lead subsidence-induced risk at in urban environments at different scales. And we are working closely with stakeholders from Emilia-Romagna region. So we are implementing a similar risk assessment methodology for the main cities of Italy. These are the 15 metropolitan cities of Italy, which as of 2023 host more than 2 million inhabitants. We are implementing a similar methodology to what was developed for Mexico. We are accounting for angular distortion and horizontal strain, as we've seen before. But I'm showing you this because, as I said before, we did it using the European Ground Motion Service that you can access for any location in Europe for free. So you can replicate this in any site of interest. So starting from the European Ground Motion Service ortho level 3 data, so the vertical and east-west displacement velocity information, we derived the structural stress in terms of angular distortion and horizontal strain. We implemented the hazard classification methodology for the metropolitan cities. And we also improved the exposure and vulnerability assessment approach by accounting for the type of building, either residential or non-residential, but also the height of the building. This information was provided by a global dataset called the Global Human Settlement Layer by Copernicus, and also the age of the building gathered from the World Settlement Footprint, another free layer that you can use for any location in the world. And we improved the methodology for exposure and vulnerability scoring using these layers to obtain detailed map of exposure vulnerability of all the metropolitan cities in this way, and implemented the risk assessment methodology using the metric and using the approach that is showcased in this slide. I'm going fast because I don't want to steal too much of your time, and we have only 10 minutes left, so I want to show you the key information. And anything else is accessible through this paper that was published a couple of weeks ago, actually. So you can freely access my paper and any details about this study, which is, honestly speaking, quite interesting and fully replicable if you want. These are examples of how the different maps look like in different zooms or 3 different cities. From this study, this is Catania, this is Rome, the capital city, and this is Naples, and these are the 3 output risk maps. As you can see, there is a combination of low, medium, and high risk zones due to a number of factors. In Naples, for instance, it's not only natural or anthropogenic subsidence. This is due to the inflation and deflation, deformation of the Campi Flegrei volcanic complex. So all of that is taken into account. So it's not just one geological process, but it's due to any differential displacement as seen from the satellite. This is the risk overview of the 15 cities, showing the amount of square kilometers involved in each risk category. As you can see, the high risk is quite limited, but even if limited, overall, these zones involve more than 2,700 buildings in the metropolitan city. So it's quite important to look at these maps in detail to see whether a particular building sector is potentially at risk or not. So for each city, the output products are maps of hazard, maps of exposure vulnerability, maps of risk, and all of them are accessible through a platform that I will point at in the next slide by providing you with the link. All these studies can be improved, spatially speaking, at city level if you have improved information at urban city blocks, and if you want to account for other exposure and vulnerability information like those provided by the free Copernicus Urban Atlas, like we did in this pioneering study in Rome, Bologna, and Florence last year. So this is another study that you can browse to get some ideas and to get some potential information of potential interest for your applications. And this is the concluding slide telling you that these risk assessment maps and the hazard and exposure and vulnerability products for the Italian cities are available in the web platform that we have developed. It's a web GIS called Control Room that you can access for free through this link to browse this sort of derived products from InSAR analysis and other geospatial layers. And these products are potentially embeddable into risk assessment workflows and mitigation workflow of the stakeholders, such as those of Emilia-Romagna that we are working with and cooperating with within this project. And they are key to convert InSAR datasets into something actionable and useful for the community. So they have the potential also to provide useful information for cultural heritage related stakeholders and users. So all the references that I cited during the slides are reported here, and most of them are open access. If not, again, you drop me an email and I can send you a copy. Absolutely, it's a pleasure. So for any of them, you can get in touch. And with this one, I've concluded part 3, so we can move to the questions or discussion. If you have any specific questions or point on this part, I'm happy to take them, or if not, you can get in touch via email or via chat here, as you prefer, as usual. Anybody? I know it's lunchtime. We are all very tired. I know it's one of the last modules for you. Many of you are in the office, so you can cannot use the microphone, but if you have questions, we can take them now. Or yeah, as I said, I'm pleased if you want to get in touch directly with me or via David and the other coordinators of the course. I'm really happy to answer any questions or doubts that you might have. And just to remind you that all the material is available in the shared drive, and I've already uploaded my slides, so you can immediately get a copy for your reference. These seminars are recorded, so you can go back to any specific part, and listen again and investigate a bit more into detail, something that you are more interested in, and see how to stimulate ideas for your heritage applications.
Hi, Francesca. Just to say thank you very much. It was very interesting to see like your methodology and all the case studies were very interesting. Thank you.
No, thank you. Thank you for being here. It's a pleasure that it was useful for you and the other students. And I hope that this will stimulate ideas. That was my goal to show you many things that could potentially open ideas for future applications. That was the point. I hope.
Definitely achieved. Yeah, very inspiring.
Okay. Okay. Thank you very much. Thank you.
If there isn't any questions, thank you so much, Francesca. And,
Pleasure.
And for the students, bueno, Francesca ya os ha comentado que eso, que se enviará también el vídeo con subtitulado en español, que ya ha subido ya la información al Drive, que también está en todo acceso, así que, bueno, sin más, pues nada, muchas gracias. Thank you so much, Francesca. Grazie mille.
Grazie. Thank you very much to you, and all the best for the next modules.
Thank you, you too. Bye.
Bye. Bye.